Hi everybody, welcome to another Chats with Chaudhry. I'm delighted to be joined today by Mike Easterling, who is the Imaging and MRMS Business Unit Manager at Bruker Daltonics. And we're going to be talking about spatialomics. But before we start talking about that, Mike, how are you?
I'm doing great, Lizwan. How about yourself?
Very well. The sun's shining, so I can't complain. It's getting a bit colder. Autumn's coming, but actually the sun's shining, so you can't complain. And actually, the last time we met was way back in Atlanta for ASMS in
Yeah,
2019,
that's right.
where you actually
That's right.
did a video with me for the Tim's Top Flex when it was launched there. And
Yep.
actually, you've done more than one video with me, because actually the year before we met at IMSC conference in Florence, and you also did a video with me there for the
That's
CIMAX
right. That's right.
MRMS. So actually, you're a video interview veteran actually doing this, although slightly different us doing a two-way conversation like this rather than having a camera in your face. So hopefully this is going to be a bit easier, a bit
Exactly.
better actually for you. I mean,
Well, I hope I come across like a veteran. I appreciate it.
I'm sure you will. So before we go on, how did that launch go for the Tim's Top Flex last year at ASMS? How's the launch gone for you?
Yeah, the launch, actually, for me personally, I have to say it was very gratifying, because we didn't want the market to sort of get the impression that we were just taking, the timsTOF Pro, right? So our premier proteomics, our premier omics machine, and just slapping a MALDI source on the side of it. That wasn't the concept or the idea that we were really promoting. It was the ability to use both sides of that machine to really do the detailed, deep omics studies and combine that with the spatial information that you're getting from the MALDI side. And so far, that seems to have resonated pretty well with the marketplace. So like I said, personally, that was quite gratifying, because I think it would have stood on its own legs, just because it is based on the timsTOF Pro. But the
Sure.
greater concept of spatialomics is rapidly gaining attention and popularity. So I think by all metrics, it was a very successful launch.
Fantastic. I'm glad to hear that. I mean, hopefully I contributed by doing that video as well. So anyway,
Absolutely.
before we start talking about spatialomics, perhaps you can give the viewers a quick overview of your business unit and your role within that.
Yeah, so our business unit is mainly focused on what we call imaging, right? So within imaging, we have the concept of spatialomics, but I think at Bruker we're a little bit unique, right? I mean, if you look at other companies, they don't have a single business unit focused just on imaging. This means that we have, a worldwide network of our employees who are imaging experts who are there to help our customers. And we're able to also network, all of these, really important customers that we have working in imaging as well. So, our business unit basically interfaces our users, our customers, with what we have going on internally in terms of hardware and software development. So, we generally manage the marketplace for imaging, MRMS, and spatialomics.
Fantastic. So let's talk about spatialomics. So,
Mhm.
we've been hearing more about spatialomics, both inside and
Mhm.
now outside the mass spec community.
Right.
So can you tell me more about what spatialomics is and why it's so important?
Yeah, sure. Before I really start to talk about spatialomics, I think it's important to back up a little bit and look at a bigger picture. And that bigger picture is that, look, Rizwan, you, me, my dog, all of these organisms are basically a sum of cellular processes. And so consequently, when we think about disease states, right, diseases are also, cellular processes. So now let's think about the way omics interrogates those cellular processes, right? So omics, proteomics, metabolomics is really fantastic because it provides a deep knowledge, but it provides a deep knowledge about the mixture. So it's a bulk analysis, right? So typically you take some tissue section and you assuming it's tissue and not plasma, and you grind it up, you homogenize it, and then you introduce it to the LC to get your information. Again, deep identification and quantification capabilities, extremely powerful. But let's go back to our concept of being the sum of cellular processes, right? When you think about what is the perspective of people who study biology, people who study physiology, and they think about disease states all the time. What do they look at? And the answer is they usually look at tissues, right? They look at tissues to really define these disease states and try to describe what's going on at a physiological level. So you see a little bit of a gap there, right? So you're doing this fantastic proteomics, and then you want to describe your proteomics in terms of disease physiology. How do you do that? And so we like to think of spatialomics as kind of a bridge that brings these two research corners together, right? And the idea of spatialomics is, you know what, I'm going to take this LC information and then I'm going to interrogate intact tissues. And when I interrogate those intact tissues, I'm going to determine the exact location of thousands of different omics components in relation to these different cells and tissue structures. And that's going to give me real physiological context. And I can apply that physiological context now to my omics studies. And at the end of the day, I think that this really allows real collaboration between people who work in the omics world and people who work in the clinical world. I recently had a phone call from one of our customers who runs a core laboratory. And he told me the story. He says, we've started, since we started doing imaging, we've been able to collaborate with a veterinary school.
Right. And
this veterinary school is looking at diseases of fetal pigs. And the information that they're providing is absolutely, it's a differentiator in terms of their ability to understand the disease on a physiological level. Look, the veterinary school could have done their own omics studies. They didn't need this core lab, in chemistry to do omics studies. Right. They need the core lab in chemistry to tell them, or to show them the distributions in tissue of these important metabolites and these important proteins that they've been, determining from their omics studies. Where are they? And so this has opened up a collaboration route that they never would have had access to, had they not started doing imaging as part of their core lab program.
Right. Okay. So does that answer the question in terms of how traditional omics researchers use spatialomics to drive physiological context into the results, or is that slightly different than when you're looking at that question?
No, well, actually, I think there's, it may seem strange at first, but there's multiple ways to do that. So, what I just did is I explained one way. So, we take the omics information and we see, exactly, where in tissue these, these different components exist. But there's another very important way that we can drive that context, and that occurs before the omics experiment, right? So if you think about it, there's several ways, as we just discussed, several ways to get tissues into the omics stream. There's this idea of full homogenization. You take an intact tissue. Inherently, there's a problem with that, right? Because you're probably only really concerned with a part of that tissue. You're only concerned with the disease state. You're only concerned with maybe the interstitial margins or something like that. The rest of it you don't care about. But the rest of it is a liability for you as a researcher, because you're getting all of these chemical signals that really don't have any relevance about what you're actually trying to study, right? There are other things. They're the stroma, they're the blood vessels. They're things that are important from a biological perspective, but not in the context of what you're trying to figure out. So what do researchers normally do? They would say, okay, I'm not interested in the rest of that tissue. I'm just going to take a part of that tissue, which is great, because you want to throw away all those signals you don't care about, because nature is complex. And we don't want to deal with nature's complexity because we'll never figure it out. So they take a smaller part of that tissue, and that's great. The problem is, let's think about a tumor, right? A tumor is not a homogeneous entity, right? It's very heterogeneous in terms of cellular phenomics and cellular structure and cellular processes. A lot of stuff going on. There's little clusters of cells, right? So this is what defines the tumor microenvironment. So as a researcher, what you would like to do is take those different tumor microenvironments and run them one at a time. Well, how do you determine where they are? You can't necessarily do that visually, right? So you can't look at a microscope and say, oh, okay, here's one section, here's the other section. You need chemical or biochemical information. And this is where imaging and spatialomics comes in again. Okay. So what you do is you run this tissue, you look at that tumor microenvironment, and you describe it in terms of chemistry. And then you get very specific boundaries and say, okay, well, here's one region, here's another region, and here's another region. You can extract those individually and then do your omics studies. Right, I mean, okay. Think about it. Manufacturers every year, make better and better mass spectrometers. Why? To give people, more omics information. Why do you need more omics information? Like we said, nature is complex. Let's cut down that complexity, get rid of the things we're not even asking questions about, and just focus on what we want to study. So actually, we've given you an application note, and I believe it's somehow attached to this interview, right? And if people want to know more about how that process worked, this was all done in Ron Heeren's lab in the Netherlands. He published a paper. We have an application note that describes exactly how this process works.
Fantastic. Well, I'll make sure that link gets added onto this video post when we put
Sure.
it up. So if we look beyond
Absolutely.
mass spectrometry and into clinically related fields like research pathology, which are focused on tissue characterization, what does SpatialOMx offer this community, and how is that different from what we're seeing from spatial transcriptomics? Easy for me to say, I understand that.
Right.
So how does
No worries.
yeah? So how does that differ though from that?
Yeah, so earlier we gave the reference, of how, spatialomics can bring together the community of omics and the people who are looking at investigations of disease pathology. But let's first just take a look at pathology, on its own. Look, a lot is expected from this field, of research pathology, and the amount of tools, some of the tools they've been using have been in place for 100 years, right? The ability to look at cellular morphology was an absolute breakthrough 100 years ago, because now you could actually, describe diseases in terms of differential cellular morphology. But things are getting a little bit more complicated, because all of the fantastic research, that's being done in for instance, cancers, right? The output of all of this research is, people are developing a lot more information, so you're getting more cancer subtypes. This is a problem for pathologists, right? You look 20 years ago, there might be 5 different types of a cancer. You take any given cancer. Today, there might be 20, 25, or 30 different subtypes. So now you're really sort of stretching the limit of what you can determine from, the traditional pathology methods, using staining or using IHC, FISH, to be able to localize where one particular protein is, right? So this is where we really see spatialomics as being a value add for this clinical community. But let's take, for example, glycans, right? It is very easy for us to run an imaging experiment for glycans, right? So we work with some collaborators, especially the people at the Medical University of South Carolina, people like Rick Drake, Anna Mehta, Peggy Angel. And so what they've shown us is, glycans are extremely specific in their ability to describe cancer states. And from the way that, tissues are glycosylated, you learn a lot about, the aggressiveness of a cancer and how you might want to therapeutically approach a cancer. Glycans are something that really, in terms of the pathology community, there's just transparency. You can image glycans as a pathologist, but you don't really have specific tools. You use lectins, which their job is just to grab onto anything, right? So of course they'll grab a glycan, they'll grab a bunch of other stuff too. So, because of that lack of specificity, we haven't really seen a lot of, glycan work in pathology space. But more and more what we see are the clinicians associated with these research pathology labs saying, look, we need therapeutic direction. We've got more and more tools available to us in terms of therapeutics, right? With all of the immune oncology that's being developed, in the cancer field right now. But which one do you choose? And this is what's really difficult, because if you, once again, going back to subtyping, you try to subtype, based on the tools at hand, and you might be able to classify 5 or 6 subtypes, not 20 or 30 or 40. And this is what the clinician needs. And so they're saying, look, we need help with therapeutic advice because we might not choose the optimal therapeutic pathway. If we could have gone back 6 months, we would have chosen a different one. That's where we're trying, we're really, inserting spatialomics as a tool, beyond, just typical clinical pathology stratification. We're moving more to real physiological determination, of what's going on, with a cancer. And, it's not being done in a vacuum either. We're really starting to think about, how we do this in a multi-imaging role. So currently, our software is able to overlay this chemical information with optical information, with staining or with IHC information, right? So you can combine, we're not saying eliminate the tools that are already there. We're saying take those tools and make them a lot better, right? So this concept of multi-omics.
Excellent. Well, there's obviously a lot going on in that field. So what do you see the future for spatialomics in terms of clinical relevance?
Right. Well, I think, as we discussed, precision medicine, subtyping, maybe even better, stratification than what's being done currently. Certainly, that would be the first reaction. And I would say also, running multimodal studies with spatial transcriptomics. We've seen a large increase or large uptake, within the community of first transcriptomics and then spatial transcriptomics. Again, exactly the same thing that we're talking about from an omics perspective, they're doing from a transcriptomics perspective. And so being able to combine that information, look, spatial transcriptomics is going to tell you, is an expression target there or is it not there? What type of cell is this? But that's where it stops. It doesn't tell you how active that particular protein is. Can you quantify the output of that protein? What's really going on there? And how has that protein been modified? Is it glycosylated? You don't have any of that information. So what we'd like to do as a value add, SpatialOMx adds that information on top. And then if you think about where the field is going, in terms of other imaging modalities, I mean, and omics also, is looking at single cell analysis, right? This is a really popular buzzword right now. But single cell analysis has the same flaw as the bulk analysis that we talked about. Throws away a lot of information, right? Rizwan, if somebody called you and said, you know what, we found this crashed spaceship in the desert. Here's a part of it. Now, what do you think this part does? You could do a metallurgical analysis. You could try to, based on the shape of the part, try and figure out, well, what does this actually do? What you would really want is to see that part working, in a network of other parts, right? And so that's really what we're doing. We're providing that interaction context. You can do single cell analysis, but that single cell just doesn't float in space, right? It sits within a network of other cells. So we want to give back that information that's basically being neglected when you do the bulk studies or when you do the single cell analysis. And then sort of I think the final, final frontier, right? So the final frontier might be, machine learning. So, pathology as more and more, they've moved to these digital platforms, and they're looking at machine learning, to sort of take over sort of the rudimentary and routine jobs, within research pathology or clinical or anatomical pathology even. And so, if we look at one of the drawbacks of machine learning is, does it have enough information to create really solid models? I mean, what does it have right now? Again, you have that optical information, so you can look at cellular morphology, and that's great. Machine learning should be able to say this cell is different than this cell in terms of the shape, the morphology of the cell. But what if we were able to give it just thousands and thousands of channels of chemical and biochemical information? Look, if you were a patient, what would you prefer? Would you prefer that machine learning algorithm to just be able to access visual information and maybe a little bit of protein information? Or would you want it to have, just an overabundance of chemical information with which to make decisions and compare, to established models?
Right. Well, obviously that is the way forward for a lot of different applications, and not just in science, but in lots of other industries as well, with AI coming in and machine learning coming into it. I suppose my only other question would be in terms of interpreting the data, because obviously you're talking about overlaying different technologies, if you like, for want of a better term, with SpatialOMx and so on. And are there people there who actually understand the data they're getting to be able to make sense of that data? So then
Exactly.
then obviously then use that in terms of machine learning going forward. That's the thing, isn't it?
Yeah, absolutely. And the tools are just getting better and better.
Fantastic. Well, that's really, really interesting. There's a lot of stuff going on, obviously, in an area I'd never really thought of before, Michael. So thank you for taking the time out to talk to me about
Yeah, you
that.
bet. You bet.
That's all we've got time for today. But as you mentioned earlier, you've got an application note that we will put up on with the video, so you can download that. And I'm sure there's lots of other information
Fantastic.
that I will add on to the post. If you've got any questions for Michael, though, please feel free to add them to the comments box below the video, because I'm sure he'll be delighted to answer them and engage with you in that discussion. But all that's left for me to say actually is, Michael, thank you very much for taking the time out to talk to me. It's been lovely to see you. I mean, as I said, last time was way back in, God, when was it? June or July last year, actually, when SMS was there. So it's lovely to see you again. It's our yearly sort of conversation, really, I think. And As always, you know, for everybody else, or stay well, stay safe, and hopefully we'll catch up soon. So lovely. Thanks for your time, Michael. Take care. Bye-bye.
Yeah, thank you very much. Yeah, cheers.